next set of signals is the complex exponential. This is really common and really confusing. It's actually not confusing when you've got the right mental image. It's hopelessly confusing until you do. Okay, so what I've written here is, this is A, and then it's the symbol alpha raised to the n. Point here is that A or alpha can both be real or complex. In general, they're complex. When I first saw this complex exponential thing when I was an undergraduate, I thought of a sequence that looked like this. And that's a valid sequence when A is real and when the magnitude of alpha is greater than 1. It blows up. But it doesn't have to blow up. It could decay. And Jeremiah, what would have to be true?
Little alpha is less than 1.
Little alpha, in particular, the magnitude of alpha would be less than 1. That's right. But here's what I didn't think about as an undergraduate. I saw a symbol like this, a signal like this, and I said, either way, it almost doesn't make sense to talk about, because one way it blows up towards infinity very quickly for positive n. The other way it blows up towards infinity for negative n. Either way, it's kind of pointless. And what I wasn't thinking about is, what if alpha is imaginary? So let me talk about that. In general, A can be, if it's complex, it can be written as having a magnitude of magnitude A and a phase of theta sub A. There we go. So we could write it in phasor notation as A at an angle of theta sub A. You can think about it on the complex plane as having a angle of theta sub A and a magnitude of A. And then this is the point in the complex plane where this is the real part and this is the imaginary part. Sometimes it's easier to think back in the way you first learned about complex numbers in high school. It has a real part of whatever this number is. You could figure it out. It's equal to A cosine theta A. And it has an imaginary part that's equal to this. That'd be A sine theta sub A. And then you could write the whole thing together as a rectangular notation of saying it's A cosine theta A plus J A sine theta A. So this is what it would look like in rectangular coordinates, where this is just one real number and that's another real number. So it's a real part plus J times another real part. So lots of different ways to think about it, but we're going to think about it in this first method. And similarly, we're going to think about our alpha as having some magnitude and some angle. And so now we're going to rewrite our sequence as being equal to magnitude A e to the j theta A times our alpha e to the j theta alpha raised to the n. So all I did here is I took what our complex exponential definitions are of A and alpha and plugged them into our complex exponential general form up here. By the way, I'm just going to put this in a rectangular block because that's an important one. And this is just going to be a little bit of derivation. So all that this means is that we can put this n inside our alpha and inside our e to the j theta alpha. And so I can do something like this. And then my e's would look something like this. J theta A plus theta alpha times n. And so now I can see that it's got this. If I wanted to use Euler's law, Euler's identity, I could say it's equal to this times cosine of everything inside here. So that would be just reversing the
Sir, quick question.
order. Yeah.
Why is it alpha to the alpha in the middle line of your equation?
Yeah, that's a good question. Thank you. What should it be?
N?
N, yeah. My pen outstrips my brain. So we get this, and then we're going to have a imaginary part that's equal to to this. All right. It shouldn't surprise us that if our A is complex and our alpha is complex, then when we put things to powers and we multiply, that our resulting sequence is complex. But if you just look at the real part, just look at the real part for a second, just at this part, you can see that it's composed of one piece here that's either expanding up or contracting down, and then it's composed of a second piece that's oscillating. And it's oscillating at this frequency with this constant offset. And if the magnitude of alpha is 1, then it either decays or blows up. It just simply looks like, the real part just simply looks like a cosine that's oscillating. So this I want you to be able to sort of see that in your mind, that this thing has a lot of different possibilities. It could also look like the real part of x of n, this cosine, this whole first part could look something like this, like a cosine, if your magnitude of your alpha is equal to 1. That's all that it would take. And it would have then it would have a frequency proportional to your angle of your alpha.